know if you're not able to see anything on your screen. Right, now today we're going to look at heat loss. Heat loss or losses in pipe and duct. So this is related to your experiment that link up with the last experiment, which is the experiment number 3, which is the flow pipe losses. Okay, so we're going to look at losses in pipe today. So we start with the heat loss. So the first equation for today will be total heat loss, HLT, which is a heat loss, will be equal HL, capital T is a total heat loss, will be equal to two components. So losses we look at for fluid dynamic or fluid mechanics, we'll look at two kinds of major loss, two kinds of losses. One is major loss and minor loss. So for introduction to fluid mechanics, this module, we will only look at major loss, which is the first component. Then when you do module 3279, then you will look at minor loss. Okay, so for this module, for your coming exam, you only look at major losses only. So minor losses will be in the next module. All right, so what is the differences between major and minor? So as you can see from the screen here, major losses is because of the friction effect. Okay, major loss is because of the friction effect, which is the surface condition of the pipe. So friction effect. Second one, the minor losses. Minor losses means the fitting, the entrance, the area changes in the pipe. So this one, minor losses, again, it will be under another module, which is the 3279 module. So you look at minor loss. So this module, we will look at only major losses because of the friction effect. Clear, Oliver and Ku?
Yeah.
Okay.
Yes, sir.
Right. So again, this module is only focused on major losses. And it's quite easy to score for this topic, where we'll look at one graph and a few equations only. All right. So since the major loss is because of the friction, we will look at friction factor. So given by this equation. So this equation on the left-hand side is pressure difference divided by rho equal to G Z2 minus Z1. This is the elevation point between point 2 and point 1 plus our major loss. Okay, so this is the second equation for today. First equation is the total loss. What is the total heat loss? Major plus minor. And then the second equation for today will be the equation that we'll use to analyze problems for this chapter. It starts with the pressure difference, P1 minus P2 divided by density equal to gravitational acceleration times your H or your elevation differences, Z2 minus Z1, plus the major losses, HL. Okay. So if your point between 2 points is horizontal, then this component will be the same. Z2 minus Z1 will be 0. So this one you can take out. So your equation will be only P1 minus P2 divided by rho equal to HL. However, in your coming exam, it won't be horizontal. It will be some angle between the pipe. So there is some value between Z2 minus Z1. So just take note on this. Okay, all right. So far, any question for these slides, these three equations? Quite direct, right?
No, sir.
Okay. So important is how you apply this this equation. So you know that P1 minus P2 is pressure differences, and previously we have a Q equation. We know that Q equal to 128 something. This one. Previously there's an equation. This one. In our power slide, this one, right? Q equal to these two equations. So we rewrite this equation in terms of P So you arrive at the slides today. All right. So this one, for laminar flow, your delta P given by this equation. Then you can write in three forms. You can either use this form, or you can change your Q with the L divided by you can transform your Q into L and your average velocity and the area that you have. All right, Q equal to VA, right? Q equal to velocity times area, cross-section area. All right, so what is important, you memorize this equation and then this equation. Then you can find all the unknown. Right? The rest is just the simplification of this delta P equation. All right, so you can either write in the first form, second form, or third form. Third form is L over D ratio format. Okay, it depends on the question that you have. So if the question gives you L over D question, then you use this equation. If the question gives you average velocity, you use this equation. Or if the question gives you the volume flow rate, you use this equation. Right, then from this equation, you can find the average velocity by link with these two equations. And then from this equation or this equation, you link with the L over D ratio. So this equation alone can ask four types of questions. One, it can ask you the pressure differences from using either these three equations. One type of question. It will ask you the delta P, pressure differences. Second, it will ask you about the average velocity by using this equation or this equation. All right, this link up with the delta P. And then the third one, it will ask you the ratio between the length and the diameter, L over D. Then you use this equation. Okay, clear, Ku and Oliver?
Yes, sir.
All right, good. So what is the equation for HL? So you know that from the equation just now, P minus 1, P1 minus P2 divided by rho equal to your major head loss, HL. So you substitute this equation into here. All right, P1 minus P2 equal to delta P. You substitute this, either these three form into this equation. All right, then you can see 32. Your major losses will be equal to 32 L over D. Mu is the dynamic viscosity. Take note. This is dynamic viscosity. V hat is the average velocity divided by D1 over rho. Recall what is Reynolds number equation. So for this module, Reynolds number is very important. So you need to always memorize what is our Reynolds number, equal to rho Vd divided by mu, rho Vd divided by mu. V here is the average velocity. Mu here again is a dynamic viscosity. You compare your Reynolds number equation and this equation here. You can write your major losses in Reynolds format. So if you rewrite the whole equation, your HL or major losses will be 64 divided by Reynolds number, L over D, average velocity square divided by 2. Okay, so these are the equations if the question asks you about major losses, and you can calculate from Reynolds number, or you can calculate from the delta P equation over here. So these slides will summarize all the equation you needed when you try to solve delta P, you try to solve Q, you try to solve the L over D ratio and major losses equation. And also from here, again, this equation is for laminar flow. This equation, all this equation for laminar flow only. So after you summarize or before you start to solve question, it's always good practice to start with finding the Reynolds number first. You find the right number, mention what type of flow you have. Do the calculation, or after you do all the calculation, confirm that the flow is laminar flow. So these are the way we solve for chapter 4. What about turbulent flow? All right, what about turbulent flow? So for turbulent flow, again, there are two sets of equation here. One set is for laminar flow, which is this slide. Another one is for turbulent flow. Now, turbulent flow, we will use this equation to find major losses for turbulent flow condition. It is given by HL, which is the major losses, will be equal to F. F is your friction factor that you get from graph. Right, friction factor that you get from the graph. Later, I will guide you through how to use the graph. L over D is from the question itself. Avalanche velocity, you calculate from your Q. Q equal to VA. So you calculate from your Q divided by 2. And your HL. What is HL? Another term. In textbook, you will have two equations. One is HL, one is capital HL. So the differences between these two is the relationship of this one. HL equal to GHL. So you substitute inside here, you get the second equation here. Both of them have the same answer. However, the first one, small HL, is the major losses with dimension of energy per unit mass. So if the question asks you to give answer of the major losses in the dimension of energy per unit mass, then you will you use this equation. If the question asks you to give your answer in the unit of energy per unit weight, energy per unit weight or energy per unit length, then you use the second equation. All right, both major losses, only the dimension of the request dimension. Clear? So if the question asks you to put your answer in energy per unit mass, you use the first one. You use the second equation, this one. If the question asks you to put the answer in dimension of energy per unit weight or length, you use the second equation. The differences is the gravity. All right, the gravity. So how do you know whether do you need to use gravity or not? If you need a weight per unit weight is gravitational effect. So there's a gravity G in the equation. Clear? So this equation, the F here, the F equation for this one, we call it Darcy friction factor. Okay, so in the coming exam, there will be one section to ask you to define, to calculate the Darcy friction factor, which is this one. Okay, Darcy friction factor, which is this one, this equation. Okay, Darcy friction factor means you will use this one. Okay, just take note on that. Again, this equation is for when the question asks you to put your answer in energy per unit mass, then you use this one. If the question asks you to put major losses in the energy per unit weight or energy per unit length, then you use the second one. Clear, Oliver and Ku?
Yes, sir.
Okay, right. So there are a few textbook that will give you more information on what is fanning friction factor. I don't want to go deep into that because it's quite confusing for this module. So when we talk about minor losses in EE 3279 fluid mechanics later on, then I will explain on what is fanning friction factor. So for this module, you only need to understand what is this equation, because this is the equation that I highlight with a mouse now is a most popular equation for this module. Okay, right. So the diameter here is for pipe. What happens if you have a non-circular duct? Means it's not a circular shape. So your D, this one, your D, you use this equation. D, you replace with this equation. D equal to 4A divided by P. What is A? A is the cross-section area. P is the weighted perimeter. So what is this one? So let me draw a diagram for you. So let's say you have a square duct and there's a flow. The flow is flowing out from the screen, right? So let's say you have a duct and the cross section is a square. The cross section is a square and the flow is flowing like that. So the flow is flowing out from the screen. So let's say you have a 2 meter, 4 meter height of object. So this is 2 meter, 4 meter. So what is the area? Area is, cool, what is the area of this object? What is the cross-section area of this duct?
Uh, 4 times 2, right?
Yeah, correct. What is the answer?
So 8.
8 what? Meter?
Yeah.
8 meter.
Meter cube.
Square. All right. Okay, so the P, what is P? P is the perimeter of this cross section. All right, Oliver, what is the perimeter of this cross section?
4, 8, 12.
12. Okay, 12 meter. So 2 times 4 times 2 times 4. Okay, you add all these perimeter together, and the keyword is weighted, means the area that touched by the float, by the float. So so if you do the calculation, if you have given these cases, 2 times 4, non-circular duct, so you 4, area is 8 divided by 12 meter. So you get the answer for D. You substitute inside this equation to find the major losses under turbulent flow. Clear? Clear, Koo and Oliver?
Yeah, sir.
Yes.
Okay, so this D also apply for laminar flow. Just now. You see this laminar flow? So this laminar flow also have D. So D you replace with the formula just now. If you do not have a circular, if you're not using a normal circular pipe, you have a rectangular or square duct. Then you replace the equation with the 4A divided by P, replace the D. Okay, clear? Huh? So this is an important side equation to replace to find the major losses. Okay, I will move a little bit faster. Seems both of you able to absorb. Okay, so this is just a derivation of it's just to prove what happens if you have a circular duct. So 4A, if you have a circular duct, your area is pi d or pi r square, pi d square divided by 4. Your perimeter is for the circle is pi d or 2 pi r, correct? Correct? Agree with this equation? Okay, then you substitute inside 4A divided by P, you arrive at D. You still get diameter. Okay, for rectangular, I already explained how to get it. So I just replace with B and H lah. So then you will use the answer to substitute in the laminar equation and turbulent equation just now. Okay, this is for major loss, major loss equation. One is laminar flow, one is turbulent flow. Okay, with that, I think we look at an example. So they are important equation. Okay, important equation. If you compare this laminar flow and turbulent flow equation side by side, it will give you the laminar flow friction factor, or Darcy factor, will equal to 64 Reynolds number. Okay, because laminar flow equation just now is 64 divided by Reynolds number, L over D, V squared divided by 2. And if you put this laminar flow in the format of F divided by LD V squared divided by 2, so you compare side by side, your F will equal to 64 divided by Reynolds number for laminar condition. For turbulent, you need to find what is F. Okay, you need to find what is F. So the next slides will be teach you how to find the F. Teach you how to find the F. There is an appendix in the Moodle. So you need to download the appendix in a Moodle, or there's a chart called Moody Chart. And this chart is called Moody Chart. So have you seen this chart before, Ku and Oliver, in other module? Have you seen this chart before?
No.
First time, huh?
Yeah.
Okay,
First time.
all right. First time, huh? So this graph is called Moody Chart. Help us to find the...
No, I don't think so. Yeah.
Okay, all right. So now we're going to teach you how to use this Moody Chart. Moody Chart is to help us to find the F. You see the axis that we have over here. On the left-hand side is friction factor F. On the below here is Reynolds number, the equation also given. On the right-hand side is the relative roughness, the E, small e divided by D. Okay, so how you're going to use this chart? The first step is to find the Reynolds number. So if you, in the exam, if you forget what is the Reynolds number, go and look at the Moody chart. Below there will be a Reynolds number equation there. So there's no reason why you can forget Reynolds number equation. Okay, so it's a rho VD divided by mu. This one you can calculate from the equation, from the problem or from the question itself. There are parameter given, you can calculate the Reynolds number. The second one, you calculate this one. You calculate what is relative toughness. You take the E divided by D. D is the diameter, or the equation that we looked at just now, 4A divided by P. That one, the D. So how you know the value of E? You refer to table 1.8. So table 1.8, it gives you the roughness of the pipe condition. So if, let's say, if you use cast iron, what is the value of roughness? Ku, if you look at the screen here, what is the cast iron roughness value?
Roughness.
What is the roughness E value? Is E value, or some textbook use this value? What is the roughness value from this table if you are using a cast iron pipe? Are you able to see the PowerPoint slides on the screen?
Yeah.
Yeah. So what is the roughness value for cast iron? I already draw the line for you.
0.00085 and then also 0.26.
So which one you are using?
I using the 0.26.
Okay, correct. So we are using the millimeter 0.26. So be careful. The dimension in this table is millimeter. So what do you think, Oliver? What do you think the dimension for the D here? What do you think? Are you using meter or diameter or mm? What do you think?
Using millimeter for roughness, should be millimeter.
Yeah. So yeah, correct. So it must be same unit. It must be same unit. If your D here you use meter, you need to convert this value into meter. So it is a dimensionless unit. It's a ratio between the roughness and the diameter. Clear? So the first step to use Moody chart to find the friction factor is to first you find the Reynolds number. Second, you find the relative roughness from table 8.1. So remember, we are using this column here, depend on the type of the material or pipe you have. Then you are seeing all these lines in the middle of the chart here. So what you do, let me see if I do some marking. Let me remove this one. So this one I enlarge the graph lah. So first let's say you find the Reynolds number. Let's say the Reynolds number I draw with the line. Second, you go to the right hand side, you calculate the roughness. So let's say we get a roughness of 0.002. So we follow this line. We will enter the graph. We will follow this line, the red arrow, and then there's a solid line there. You follow this line. And then intersection point, you stop there, right? Then you use your ruler to draw a line over to the left-hand side. So the value that you see on this axis is the friction factor that you can use to calculate the major losses just now, the F value. So this F value, what is the application? You substitute in this equation, right? You substitute in HL equal to F L over D V squared divided by 2. This F is from Moody chart. Okay, this one is from Moody chart. Clear? Cool, clear? How do you know how to find F from Moody chart? First, Reynolds number.
Yes.
Second, relative roughness. Then you join the line together. You draw then the intersection point. You use a ruler, draw across. You find the F. Then use the F to do the calculation for the major losses. Quite direct, huh? So there are two more. Okay, there are two more equations that you can use, right? You can use to find the F. Okay, if you are using Moody chart, we call it graphic method. If you're using Moody chart, we call it graphic method. Means you use graph to find F. Another method, we call it analytical method, where analytical method means you use formula to find the friction factor F. If you are having a laminar flow condition, your F, you use F equal to 64 divided by Reynolds number. Then you use this F, substitute into the equation for major losses. You use this if you have a laminar cases, you use this formula to find the F. You substitute this F into this equation. HL equal to F, L over D, V squared divided by 2. You substitute F equal to 64 Reynolds number inside here to find the major losses for the system. So if it's a turbulent flow, then there's another equation to find the F here. There are two methods to find the F for turbulent or laminar. So the F is through Moody chart, we call it graphical method. Second one, analytical method, which is I'm going to show you the equation, which is the one that you see on the screen here. All right. I not expect you to memorize this form, but you should have this equation somewhere in your notes when you come to final exam. Because there will be a section ask you to analyze using two methods. One is using Moody chart. One is called analytical method, means you use this formula to find the F. Understand, huh?
Yes, sir.
Yeah. So I need to brief you a little bit on this formula. So this is 1 over square root of F equal to minus 2.0 log. And this is the roughness, the circular roughness from table just now, divided by D divided by 3.7 plus 2.51 divided by Reynolds number times square root of f. So if you need to use this formula, you need to calculate the number first, and then you rearrange the equation in terms of f equal to what? Then you calculate. Normally, the f that you calculate will be very, very near to the Moody chart that you use. Let's say your Moody chart gives you 0.25. The equation that you use over here, either the top one or the bottom one, will be very, very near to 0.025. So again, there are two methods, just a reminder. There are two methods to find friction factor. One is through Moody chart. The chart alone, we call it graphic method. Second one is analytical method or mathematical model, which is these two equations. One is for laminar flow. The above one, 64 divided by Reynolds number. That one's for laminar flow. The bottom one is for the turbulent flow. Clear, Ku and Oliver?
Yes, sir.
Okay, let's look at one example. Okay, so this example, let's say you have a pump and the tank, water tank there. So you have a 0.1 and 0.2, and the height is given at 0.2 is 10 meter. The length between the 0.1 to the control volume, the big tank is there, is the L equal to 100 meter, and then the Z direction is given there. Okay, so you have this condition, and the volume flow rate is given, as you can see from the screen here. The volume flow rate is 0.01 meter cube per second. Okay, so we need to determine what pressure must the pump produce at the pipe to generate the flow rate Q 0.01 meter cube per second. And you're given the diameter of the smooth pipe. You're having a smooth pipe here. So smooth pipe is 75 mm. And for this module, we only consider major losses in the calculation. How do we solve this kind of question? The first step, you always write all the parameters given. All right. So we are going to use the first equation. You write Reynolds number on your answer sheet. Straight away, you get 1 mark for the Reynolds number equation. Reynolds number equal to rho VD divided by mu. So these are the 3 marks area. So you write Reynolds number, you get 1 mark. Second one, you write out the major losses equation. You get another mark for that. So there are two types of equation. Remember, just now you have a laminar flow equation and turbulent flow equation. Then the rest is just substitution of value. There is another equation. You write P2 minus P1 divided by rho equal to HL. Yeah, so basically these two equations is sufficient to find the major losses. However, you need the third equation, which is P1 minus P2 divided by rho equal to major losses. You need this one. Okay, the delta P equal to P1 minus P2, which is equal, the P1 is your pump. P1 is your pump pressure. P2 is 0 gauges. P2 is 0 gauges. We already covered this topic, why our P2 is 0. Oliver, you can recall why do we put P2, although P2 is not given, but do you understand why you put 0 here?
Was it related to the frictional force and something about the Newtonian fluids?
Okay, why at this point your P gauge, your sensor gauge equal to 0? You understand? Do you guys understand? The surface exposed to what? Yeah, correct. Exposed to atmospheric pressure. So you imagine you are holding a sensor, a pressure sensor. So you stand at the surface there. So the sensor will show 0 because there's no pressure difference. But if you go down into the water, then you start capturing reading from your sensor. Does it make sense to you?
Yeah.
Yes.
Yeah, okay, good. Then the next one is the substitution. So you use the third equation that you see on the screen here, this one. So your P1 is pump, P2 exposed to atmosphere, so 0. Then you pull the density to the right hand side, so P pump equal to rho HL, because this question asks you to find the pressure of the pump. So this is the equation that we're looking for. All right. Then you check the Reynolds number for the type of the flow. So you recall the Reynolds number equation, you substitute the value. So again, there's a table for water. Water parameter changes to the according to the temperature. So we assume water as 20 degrees C. The rho will be 999 kilogram over meter cube. Dynamic viscosity is 1 10 power negative 3 meter per over meter dot second. So this is from table. You refer to appendix also. So how we calculate the average velocity from the Q? So Q equal to VA. You rearrange the equation. You are given the Q value. A here is the diameter. So rho VD square. So you see this one is through this smooth pipe here, 0.75 meter. So you use the diameter of the small pipe. Okay, diameter of the small pipe. So you change everything in the unit SI. Then you're able to find the average velocity. In this case, reference answer will be 2.26 meter per second. Then after that, you substitute inside the Reynolds number equation. You're able to find the Reynolds number. So if you calculate the Reynolds number, you will get 1.79 10 power 5. Okay, so cool, what is this Reynolds number tell you? Do you having a laminar flow or turbulent flow? And why? You still remember the magic number that I asked you to remember? Reynolds number? The 4D number. 2 what?
2,300.
Yeah, correct. 2,300. So this number is more than 2,300. So it's under what kind of flow?
Laminate.
Limit. Is more than 2,300, you get limit. Oliver, do you agree with this statement?
No, Laminar is below 2,300.
Yeah, so if you have a number, Reynolds number less than 2,300, you're having a laminar. So
Yeah.
based on this screen, the Reynolds number is 1.7 10 power 5. So this number is more than
More than
2,300.
2,000.
So it's under turbulent flow.
Turbulent.
So on the screen here, you have two equations to choose. One is laminar flow and turbulent flow. So you are looking at the second equation here. Okay, and you look at the equation here, there's one parameter that is missing, which is the F here. This one is missing. So again, this Darcy friction factor F, there are two methods to find. Graphical method using Moody Chart. Another one is using the equation just now. Right, the log equation just now. So just repeat what we have covered just now. How do you find the F for this equation? So you already have the Reynolds number. Okay, you already have the Reynolds number. So on the Moody chart, you write Reynolds number 1.7 10 power 5. So you go and find where is this location about. It's somewhere here. Okay, so how do you read this axis? So you see, this line is 10 power 3, which is 1 times 10 power 3. This 10 power 3. This is 2. Okay, so this is 1. Okay, let me write here. This point, This is 1 10 power 3. Then this one is 2 10 power 3. So what do you think this value, this line mean? Cool. What do you mean? What do you think? What does it represent? This line, this location. What does it mean?
Um, 1.5, right?
Yeah, 1.5, what, 10 power?
1.5 10 power of 3.
Yeah, correct. So you know how to read from here. So you look at the below there, the Moody chart there. So you are having 1.7 10 power 5. So you look for 10 power 5. So this is 10 power 4. 10 power 5 is here. Then this is 1. This is 2. So this is 1.5. So it's around here. Around here lah. Understand? Agree? Both of you, Oliver and Cook? You agree that this red line is around 1.7. But this, it should be a little bit to the left lah, because of the Excel PowerPoint format. I'm not able to put the line according to the position there. But the concept is there. Huh? Then the first step, you already find the Reynolds number. You draw the line. Then after that, you determine the right-hand side, the relative roughness. So we are having a smooth line. We're having a smooth line just now in the statement. Huh? In the question statement, you see, we have a smooth pipe. So smooth pipe, in the Moody chart there, there is a line for smooth chart. There's a line for smooth pipe. Okay, there's a line for smooth chart. So after that, you draw the line, you calculate you actually don't need to calculate the roughness here. You straight away look at the smooth pipe line that I highlight just now, and then you use your ruler to draw a line to the left to find the F. This is graphical method, yeah. Oops. So you draw to the left, you get around, this is 0.015. This is 2, so you have 5 lines here, 1, 2, 3, 4, 5. So you have, in this position, the value will be 0.016. Agree? So both of you agree that we are our arrow here pointing to 0.016.
Yes.
Agree, huh? Okay, so we'll use this value to find our major losses, or we use this value to find our pressure of the pump. All right, so or you can use these two equations. So again, the first one we cannot use because the Reynolds number is more than 2300. We use this one, analytical problem, to find the F. So you substitute the E here. So for smooth pipe, the smooth pipe, let me see, there's a in table. Okay, this table do not have the smooth pipe. Yeah, there's F. They have. So you can see here, there's one column there. At the below here, you see there's a smooth brass, copper, or plastic pipe. So there's a smooth word here. You can use 0.0015 to calculate the value. Clear? This value, if you have a smooth pipe. You look at the table. Clear? Ku and Oliver? Right. Yeah. So after that, you just substitute back. So P pump equal to rho HL, and you substitute the equation inside there, substitute all the value, you're able to find the pressure of the pump will be 1.53 10 power 5 Pascal, Newton over meter square, and this is a gauge because you're seeing gauge. Huh? Okay. Can you guys go for one more example? Then we call it a day.
Sure.
Sure.
Yeah, okay, one more example. All right. So let's say we have a question, something like that. You have a pump on the left-hand side, and then again, our equation here, we look at the friction. So you have a crude oil flowing through the pipe here. So you have 2 point, 1 and 2. So point 1, okay, let's read the statement. Crude oil flow the level section of the pipeline, rate 1.6 million barrel per day. So 1 barrel equal to 42 gallon or 2.94 meter per second. Right. So the pipe inside the diameter is 1.2 meter. The roughness is equivalent to galvanized iron. So this one you refer to the table. The maximum allowable pressure is 8.27 megapascal. The minimum pressure required to make sure the flow is flowing is we must more than 0.35 megapascal. The crude oil have a SG, specific gravity, 0.93. So you see specific gravity, you need to convert this one in with the water density. Viscosity is given at 60 degrees C is given. So for this condition, determine the maximum possible spacing between the pipe section. So this, you see, this question asks you about L over D kind of question. The length, L over D kind of question. If the pump efficiency is 85%, you need to determine the power that must be supplied at each pumping session. We consider the major losses only. Okay, the efficiency is 85% or your efficiency equal to 0.85%. All right, so how we solve? We need to find two things. One is maximum spacing, which is our L. The second one is the power. So governing equation, first you find the Reynolds number first, rho Vd divided by mu, and you write these two equations, laminar flow, this equation, turbulent flow, this equation. So from the Reynolds number, you can determine which formula to use over here. And then another equation, P1 minus P2 divided by rho equal to HL. This equation only apply for level pipe only, for level pipe. So if you do not have a level pipe, you need to use the original equation with this one. Okay, P1 minus P2 divided by rho equal to Z2 minus Z1 if you do not have a horizontal pipe. So in final exam, most probably you won't have a horizontal pipe. Make sure you use this equation to find the answer. Take note, clear? Cool and Oliver.
Yes.
Okay, don't make mistake. Don't show this mistake. I already mentioned to you already. All right. So once we have all these equation, let's solve. So the Reynolds number, rho Vd divided by mu, we don't have the average velocity. So, but we have the Q. We have the Q in the question. So Q equal to VA. You rearrange the equation, you're able to find the average velocity. All right. Yeah. The D you have, D is this pipe. So given by this one, you're able to find the average velocity. So substitute this answer inside there, you're able to find a Reynolds number. Compare this Reynolds number with 2300, less than 2300, laminar flow, more than 2300, turbulent flow. Okay, you're able to find Reynolds number. Second one, you find the from this equation, P1 minus P2 divided by rho equal to HL. HL is the major losses. You rewrite P1 minus P2 equal to rho H1. So not H1, HL. Major losses, you substitute the equation. Right? The equation of F, L divided by D, V squared divided by 2 in the equation. And then you use the table from the Moody chart to find the F, right? There are two methods. One is graphical method, one is the analytical method. In the exam, you need to show the differences between these two. One you use Moody chart, another one you use a formula to find the F. What is the differences between these two? Okay, you need to find the differences between these two. The rest is just substitution, right? The rest is just substitution. The question asks us to find the length. So you rearrange the P minus P2 equal to rho FL over D V squared divided by 2. We are interested to find the L over here. So you rearrange this equation equal to P minus P2 times the D divided by FP2 divided by this one. Okay, so I think the formula is not properly written. It should be have a bracket here. All right. Okay, then you continue. You can find the L. Is that clear for you? Is that clear to find the L? Anything that doesn't make sense to you, let me know. Okay, yeah?
Yeah, okay.
Okay, Anna, Oliver and Ku, no problem, huh?
Yeah, no problem, sir.
Okay, good, excellent. So the next one, we want to find the power. You are given the efficiency. So what is efficiency? You learned from thermodynamics already. So efficiency equal to input divided output divided by input. Output divided by input. So output power divided by input power. So recall in your thermodynamics, your power of the pump equal to Q times the pressure difference. So this is the, I think, just a recall this equation. You need this equation for your final exam. So your power of pump equal to Q, your volume flow rate times the pressure difference. All right. So just now you're able to find the pressure difference, right? So you're able to find the pump over here. So from here, your pump in, which is your supply power, equal to your pump. Sorry, I think something wrong with my equation. Okay, my equation is wrong. It should be, this one should be, yeah, correct. Yeah, correct. So you double your power in equal to your pump power divided by your efficiency. Okay, by using the efficiency equation, your input divided by your output divided by input. Output divided by input. So you rearrange the efficiency equation, you're able to find what is your required power. Okay. So you can see here the pressure difference here. The delta P, you take this one minus this one. Clear, Oliver and Ku? The delta P here, you take the maximum pressure minus the minimum pressure. You get delta P. Then you times the volume flow rate. You get the power of the pump. Then you need to find the power needed. Power needed, you use the efficiency equation. You find the power, the required power for input. The unit is in kilowatt or watt, or in a watt. Clear, Ku and Oliver?
Yes, sir.
Okay, then the next question, I will just give you as a homework lah. This is the same principle, the same scenario, and then you have the pressure difference bridge both end, and then they ask you to find the standard pipe size, which is D, or L, or the L is given. So now you find the D. Same principle you find. Okay, treat this as your homework to practice on the equation that we learned today. Okay, with this we summarize chapter 4. Let me stop the recording.